Welcome to Integrated Math 3. On this episode, Stevenson will demonstrate
We've been studying polynomials for a long time now, for the past 3 to 4 weeks. Now we get to finally venture into our new family of functions. And the way we're going to do that is by taking something that we know and doing its reciprocal. For example, y equals x is the identity function. It's the line that you like to draw that's just like goes right down the middle here, right? 1, 1, 2, 2, 3, 3, and so forth, okay? But what happens if we take that function and we do its reciprocal? In other words, what if we take all these values and we flip them? Well, what we do is we in turn create what is called the parent reciprocal function, or the parent rational function, which is known as the reciprocal function. What we're going to do is take each of our values and do its reciprocal. So if I take negative 3 and I put it in the denominator, it's going to become negative 1/3. If I do negative 2 in the denominator, it's negative 1/2. If I put in negative 1, it's negative 1. Now, if it's a fraction and I'm doing the reciprocal of it, it just flips into the other way around, so this has become negative 2. And if I do negative 1/4 and I do that reciprocal, it's negative 4. Now, if I put in 0, this is undefined because I end up with 1/0. Okay. Now, if I put in 1/4 because I'm doing reciprocal, then it ends up being 4. And if I put in 1/2 into a fraction, it's 2. And if I put in 1/1 is 1. And if I put in 2, it's 1/2. And if I put in 3, it's 1/3. Now, before I graph this, notice, as I'm getting closer to 0, do you notice my numbers are getting larger? In this particular case, they're becoming more negative. In this particular case, if I'm going towards close to 0 from the positive side, notice they're becoming more positive. And 0 is undefined. So what does this look like? Okay, let's start here. Negative 3 is negative 1/3. Well, if this is 1, this is negative 1, 1/2, so it's maybe somewhere around there, okay? Then negative 2 is negative 1/2. And then negative 1 was negative 1. And then negative 1/2 was actually negative 2. And then negative 1/4, I'm going to have to approximate here, is actually all the way down here to negative 4. So if I connect it, it's going like this. And it's actually avoiding the y-axis. It does not want to touch it at all. Let's try the other side. So if I start with positive 3, it's 1/3. It's 1/2. I don't know, maybe about there. Then if I do positive 2, I'm at 1/2. And if I do positive 1, I'm at 1. Notice as I'm getting closer to 0 from the right side, the positive side, it's getting larger. If I do 1/2, it's actually 2. If I do 1/4, it's all the way up here at 4. And again, it's avoiding the y-axis. This is our rational function, known as the reciprocal function. It will avoid the y-axis at all costs. It will never touch the y-axis without transformations. This is our new parent function of our rational function family. These pieces will not touch, okay? Now, let's look at our characteristics of this. What does the domain appear to be? Well, the domain are all the x values. So let's look at our graph here. We can put in negatives, we can put in positives. What's the only number we can't put in? And that's 0. And we can see that in our graph because as we get closer to 0 from both sides, do you see how my graph is avoiding, it's bending, it's curving away from that y-axis? It cannot be 0. So our domain is all real numbers except 0. So I'm going to write this 2 ways. I'm going to write it out in words. So I'm going to say all real numbers. Now, another way I can write it is using inequality or interval notation. Let's practice interval notation. So what I would say is from negative infinity up to 0, but don't include 0, right? We can't actually use 0 in our domain. Union, and then starting on this side, 0 to positive infinity. This is how I'd write the domain. Now let's talk about the range. Let's look at these y values. The y values are this way. So the graph compresses and goes towards 0, but then notice what is it doing? It is bending and going towards the x-axis. It is going super close to that x-axis, but it will never touch it. So again, we have a very similar instance where it's going to be all real numbers except y cannot be 0. So again, I'm going to use interval notation, and fortunately in this case, it'll look exactly the same as this. Now, let's look at x-intercepts. Well, this graph will never cross the x-axis. No matter how negative my input is on the left or how positive my input is on the right, this graph is going to get super close to the x-axis, but never touch it. Think about it. If I pick a fraction like -1/8, it's just going to be 8, -8. If I do, 1 over 16, it's just going to be positive 16 because I'm going to put it in this fraction, and a fraction within a fraction does the reciprocal. So this x-intercept will have none. Let's look at the y-axis, the y values. We can see here that with the y values here, again, it's not going to cross the y-axis. The graph is going to bend away from this y-axis as much as possible and never touch it. So this will also not have any y-intercepts. This is our parent function, keep in mind. If we transform this in any way, these characteristics can change. Now, something new, a vertical asymptote. So a vertical asymptote is a vertical line that the graph will not touch. It is attached to your domain restrictions. So the vertical line in this case is going to be the vertical line x equals 0. So your domain restriction right here is your vertical asymptotes. There are exceptions to that rule, but right now for our parent function, this is where my vertical asymptote is, and we draw it by doing a dashed line, just like that. Lastly, we have what's called the end behavior asymptote. So now we know about end behavior. We know how to describe it. We look at as x goes to positive infinity, what is the graph doing? And as x goes to negative infinity, what is the graph doing? But with polynomials, remember it was always going to an infinity, right? It'd be like positive or negative infinity. With rational functions, that's not the case. With rational functions, your end behavior asymptotes are actually values. It's not an infinity. So if we look at this case, as x approaches positive infinity, what are your y values doing? So let's look. As x is approaching positive infinity, so we start here, notice what are the numbers doing? They're getting smaller and smaller and smaller. What are they going towards? 0. Let's look at the negative side. As the inputs on x go closer to negative infinity, what is the value doing? Well, look at the table. The x values are getting smaller and smaller, again closer to 0. So what this means is this end behavior asymptote is another dashed line. Now, the graph can cross it, okay? Be very careful with this. All it means is that at the ends of the graph here, that the behavior of the graph is approaching a horizontal line, y equals 0.